Okay, so on the PDF, this is new. These are learning objectives. This is what you're going to be assessed in as per College Board in May. So they're at the top of the PDFs, and that's going to go from here. You didn't have them for Chapter 1 because there are no Chapter 1 questions on the AP test. But when you look at this at the top of each PDF, take a moment to read this stuff and say, by the end of the lesson, that should make sense to you what that says. If you're looking at something and said, I don't even know what this means, then we have a problem. So example 1 is this, and you've seen problems like example 1 for a long time. It says a rock breaks loose from the top of a tall cliff. What's the average speed during the first 2 seconds? So the average speed in the first 2 seconds, okay, you've done this in multiple courses where you have -1/2 times 32 t squared. It's -1/2 times the force in gravity per second squared, plus the initial velocity, plus the initial height. So you look at this problem, you don't have initial velocity, it just falls. You're not spiking the rock. There is no initial height because they're saying how far did it fall. So you're measuring the positive distance, how far it fell. So we don't need a negative here. That's why it's not there. Because if you put -16 x squared in this mode, plus the initial velocity plus the initial height, then this function would give you how high the rock is off the ground, because this would be negative and it would be falling against that initial height. All we're measuring now is what the slope of this curve is. Okay? So in order to get the slope, we're going to do this. We have this table. And we have the initial value x. We have f of x. And we're going to change, going to h units to the right, just like we've been doing. We're going to slide the graph h units to the right, replace x with x plus h. Because we're not, well, you would say, you said replace x with x, subtract h. That's in the function itself. If we had y equals screen, this is what we have in the table. And then f of x plus h. We want to do a difference quotient. So I have it right here in y3. You're going to put it in y5. So I'm going to walk you through that. You go to y equals, and we're going to put this in y5 together. Ready? Open parentheses. Vars, y vars, function mode, y1. Open parentheses, x plus alpha h, close parentheses, subtract, vars, y vars, function mode, y1 of x, close parentheses, that's the numerator, divided by x plus h, take away x. So the x's are going to subtract to 0. I'm just going to divide by alpha h. And what the point is, this is based upon what you have in y1. So you can just have this out of the way, turn it off, and when you need the slope, the instantaneous slope of y1, you turn on your y5. So I'm going to go back here. And I have it in y3, it doesn't matter. So now on the home screen, you're going to do this. On the home screen, you type in 0.001 store alpha h. So you were putting in a small value for h. And all those green letters on your calculator give you an opportunity to store values in there, and they stay there till you type them over with something else. So then I typed vars, y vars, function mode. Now you would do y5 because that's where you have it. and make 2 the input. Now, this problem's a little deceiving for example 2, because they said, example 1 said, what's the average change from 1 to 2? So the average change, I would do 64 take away 16 over 2 take away 1, right? And you would get 48 feet per second. But the instantaneous change right at 2 seconds, we're using this, and we get a small value for h. And what's deceiving about it is y5 is giving us the same output as y1, except for this residual over here. So this is telling us, ready, because h is going to 0. We want h to be a minimal amount. And because we quantified it, we have an error here. We'll deal with the error moving forward. But the point is, this rock is traveling at 64 feet per second at exactly 2 seconds. And what you've done is what we're trying to do in the whole course. Well, half the course. We're trying to find the slope of curves. And what's challenging about that is the slope of curves is changing. Slope of a line is constant. It's the same thing. You know, that's what you do that in middle school, but the slope of a curve is changing. So all these numbers to the right of decimal point are errors. And like I said, we'll deal with that. But you're going to use this. You have to understand this, where this is coming from. This, what you have in Y5, what I have in Y3, is coming from this T-chart. It's subtracting up. This take away this, the difference of the Y's, over this take away this, the difference of the X's. Okay, so that up there is your model, and you go to problem number 3. We're not going to give you a lot of time to do example 3 because the answer's right here. Here's the table. They want to know what the speed is, what the velocity is at time 3. So that what that means is this. When I look at this table, we did 2, ready? At 2, the rock had fallen 64 feet after 2 seconds. Its velocity was 64 feet per second, which, like I said, was misleading. When we get to time 3, the rock has fallen 144 feet, and its velocity is 96 feet per second. It has accelerated between 2 and 3 seconds. It's traveling faster. Okay? So if you're looking at this T-chart right here, it's an H chart, ready? You have the input, which is time in seconds. You have the output, which is how far the rock has fallen after that many seconds. And you have the velocity in Y5, which is how fast the rock is falling at that specific second. Keeping in mind we have this residual because we based our calculation on H being 0.001. But all of this comes back to you making a connection between this table right here and your Y5, which is your difference quotient. Suppose you accidentally delete Wi-Fi. Well, you should be able to put it back in yourself because you're just saying, I'm subtracting the difference of the Y's over the difference of the X's. Now, if you look at the PDF, what happens is I jump from example 2, or what we're going to do today, to example 8. We can't have that. I mean, the point is, if you're in the textbook, go to page 60. I need you to fill in some of this material because I'm highlighting the most important examples. I'm leaving stuff out because if I just talked at you for 48 minutes, your head would be spinning, right? So we're trying to balance this and keep pace to cover the material we need to do by May. So some of this, you need to be looking at the book, balancing that with the PowerPoints, the narration or not, and saying, well, this isn't the most important thing, but this is, something I'm accountable for. So you're not going to graph this, just look up here. I go to y equals. And I'm going to draw the picture that's in the margin on page 60. On page 60, you have this. You have sine x divided by x. Now think about what that means. It means the sine wave divided by the input. So as you go to the right, all your heights are going to be divided by how far you went to the right. And this graph, as you go to the right and left, is going to get closer and closer to hugging the x-axis. And there's your picture, okay? But what we're really concerned about is this right here, the behavior of the graph at the y-axis. It appears to be equal to 1. But if I go here, second format, and I scroll down and turn my axes off, it's not equal to 1. There's a hole in the graph. We have discontinuity. And the reason you have a hole in the graph is because you can't divide by 0 until you get to chapter 8. So we can't divide by 0 here. So this graph has no value when x is 0. But conceptually, what we're saying to you is this. As your x's go towards the y-axis from the left and from the right, the graph is trying to get to the same place. From the left, from quadrant 2, the graph is trying to climb to 1. From quadrant 1, if I'm going right to left, it's trying to climb to 1. It's just not going to get there. And the fact that it's trying to get there is a big deal. That's the concept of a limit. So they have a table in the margin on page 60. So we show you the same thing. So you get an error message at 0. But here these numbers, starting at -4/10, are getting higher towards 1. At 4/10, as you go to the left, they're getting higher towards 1. And you can make this delta table smaller, and they would get closer in there. But it's not going to take on the value of 1 because you can't divide by 0. And that's conceptually what we're dealing with when we talk about limits. So here's example 5, which is We're not going to go over it, but you can read this and see if it makes sense to you. There's a little bit of algebra I took, tangent, rewrote a sine over cosine, took this x and wrote as 1 over x. That describes that behavior of this graph right here, the sine of x divided by x. This is more important. This is example 8. So in your textbook, I'm on page 64, but you don't need to go to 64 because I have the picture here. And this is a piecewise linear function. Ready? So just look at one piece of it. Between 0 and 1, you have a linear equation. It's what? It has a slope of -1, and the y-intercept is +1. So that's the slope, I'm sorry, that's the equation of the line, just that one part from 0 to 1. And then you have these additional parts. Piecewise linear, that's not as important as what we're going to use it for. So take a look at this question. It says the limit as x goes to 1, and look at this superscript, from the left. The negative superscript is telling you from that direction. Not towards the negative direction, from it. It's like wind speeds when you watch the weather on TV. If there are easterly winds, that refers to those winds coming out of the east. They're heading west, but they're not called westerly winds. They're called easterly winds. Same thing here. The limit as x goes to 1 from the left. The height, f of x is the height, does not equal the limit as x goes to 1 from the right of the height. So we're right on the axis. I'm going towards 1 from the left. The height is going to 0. Now I'm going towards 1 from the right. The height is going to 1. They're not equal. I move on to 2. As I go towards 2 from the left, the height is trying to get to 1. It is 1 from the left. As I move towards 2 from the right, the height is going to 1. They're the same. The limits are the same, but the function's not equal to 1. If you put 2 in the function, it gives you this closed dot up at 2. Look at 3. As x goes towards 3 from the left, the graph's trying to climb to 2. As x goes to 3 from the right, it's trying to climb to 2. So the limit from the left equals the limit from the right, and it also equals the value of the function. So the reason we went here to example 8 is because this picture is so helpful. You have 3 different things happening at 1, 2, and 3. At 1, the limits are not equal. The limit from the right equals the value of the function, but the limits aren't equal. At 2, the limits are not equal, but the value of the function. I'm sorry, the limits are equal, but they're not equal to the value of the function. And as x goes to 3, all 3 things are equal. The limit from the left, the limit from the right, and the value of the function. So I'm leaving that up there. That's your model. Now, ready? This is important. Ready? You have to understand the pictures. We do the pictures early in the course. You come back to them the entire time. There were pictures on the AP test in May, the abbreviated AP test. They gave you pictures. If you have trouble understanding how these graphs are related, these pictures, you're not going to get your goal. It's just, you can't do it. You can't overcome an issue with the pictures. Okay, so it sounds easier than it is. I just have to deal with pictures. But you have to get your mind around what the picture's about. So I'm going to leave that up there, and you're going to problem 37, please. Okay, get a 2-minute warning. You might not finish the whole thing, but 2 more minutes, you would put a dent into that picture for problem 37. Now, we're going to go over this, but I want you to keep this in mind because I was just on Khan Academy looking for BC children had their test today on limits, on chapter 2. And some students are going to have to be remediated. But I was going through that and looking at or perusing some of the videos. That's instead of doing problems, you might do a couple problems and say, I'm going to watch a Khan Academy video to help me understand this. You have to take ownership of this. What's going to help you understand the material? It's not just, ready, doing 1 to 31 odd. Those days are long gone. All right. So we look at this. And A, B, D, E, and F are true. The others are false. So pick one true one and one false one, all right? So B says, the limit as x goes to 0 of the function is 0. As x goes to 0 from the left, the height's going to 0. True. Then E says, the limit as x goes to 0 with no superscripts. Well, E's true. Why? Because the limit from the left and the limit from the right are the same. So you can drop the superscripts. But if you look at 1, the limit from the left is going to 1, and the limit from the right is going to 0. So they don't have the same limit. And that's H. H says the limit as x goes to 1 is 1. No. As x goes to 1 from the left, it's 1. But as x goes to 1 from the right, it's 0. They don't match. So the limit is not equal to 1. In fact, the limit doesn't exist. Okay? And then example 9, which we're not going to deal with today, but we'll come back to what this means later. So I'm going to send you a